RoboJackets training. Today we're going to be talking about like different processes like for machining, right? This is a really important aspect of design. Whenever you design anything, be it RoboJackets or, in industry, you have to take into consideration how you're making that part. So this is just kind of like a cursory overview of what you can do on the machines we have access to, and I guess like how you can design around them. So first, all right, a couple considerations with how you're making something. So when you're designing for manufacturing, you have to understand what each machine does, right? And what their limitations are, be it like what they actually physically do to your part or the tolerances involved. And we'll get to that in a little bit. Also, another thing is like if there's a process that seems necessary but can't be made in-house, you can always outsource it to someone that can do it. So for example, I know BattleBots heat treats their drum weapons, right? For a lot of the time. IGVC, RoboNef, sorry. I'm an old person. It used to be called IGVC. RoboNev outsources a lot of, I guess, welding and I guess coding work to ProtoCase. And of course, RoboCup outsources the most. Like they have a lot of small components that need to be made repetitively, so it just makes sense for them. So, okay, like the first thing I'll go over real quickly are just like the basic machines you see on here. On the left, you have a vertical bandsaw. So it's just a running blade that keeps going, and you just push your material in there, and it's used for like any like sort of 1D cutting. It's not very good if you want to be super precise, but it gets the job done if you need something to just be like quick and rough, right? The second one over here is called the Sandblaster. We do have one in the SEC, but I'll be honest, I don't think I've ever personally used it. I'm not sure if other RoboJackets teams use it, but it's still something that's worth considering, especially if you want like a rougher surface finish on whatever you're working with. And the final one on the right is called a horizontal bandsaw. So just like in the vertical bandsaw, you have a what's it called? A belt with some bladed edges on one side, and because you can actually like what's it called, vice down whatever part you're working with, those cuts will be pretty even, and yeah, it's really useful for cutting down really large chunks of like aluminum or steel or what have you. Some other ones, right, and these are the ones I'm going to be talking the most today, are you'll see on the left, that's called a mill, right? So in a mill, I'll get into this a little bit more later, but essentially you have a, you know how like in a drill press you have your drill bit, and that's what rotates around, right? So likewise in a mill, you have that staying stationary and rotating that tool, and you have a bed underneath it for which you can actually move the part, and that's where you can get some pretty crazy geometry, and it's really useful. The second one you see on here is called a lathe. So this is for like any axisymmetric parts. So instead of rotating the tool, you're rotating the part itself, and then you can do a whole bunch of operations to it kind of axisymmetrically, whether it's like boring a hole or just cutting some grooves around it. And the last one you see on the right is called a Waterjet. It does the same thing as a laser cutter if you're familiar with that. So essentially it just like pushes a great burst of pressurized water and garnet into whatever part, and it's really good for doing some quick precision cuts on like on any materials that you're working with, right? And it's for 2D parts. Now the advanced machines, and I'll be covering them a little bit closer later. The one on the left is called a CNC lathe. So like in the lathe that I described earlier, it has the same functionality, except this one you can program using like CAM software to actually like cut out like more complicated grooves, but you can do the same things that you can do in a manual lathe, except you can get fancy with it. The one on the right is a CNC mill, and just like in the manual mill, you can cut out a whole different types of geometries, and we'll get into more of what that does later. But again, you can program it to get some like really precise and neat geometry. So first, machines. I'm going to show you a couple of videos. This is my favorite part, right? If you ever want to like waste some time, either if you're procrastinating or just like you have nothing to do, which at Georgia Tech is a rarity, but you can always use it to procrastinate, is just watch machining videos. The first one is going to be a mill. So we'll just watch a little bit. So like right over here, you have that tool that's spinning, but then you're actually moving the bed underneath it. And I guess the tool also moves in this case, but Yeah, you can get real fancy with it, and it's super satisfying. Look at that go. Yeah. Okay, so now let's go to the lathe. The lathe is super fun. All right. This one's great. I think they're cutting out a chest rook using a lathe. Give me a second. Why isn't it playing? So like over here, they have that tool that's just cutting out whatever groove you need. And you can see this is like for any axisymmetric part, right? This is always super fun to watch. Yeah, that's pretty much it. And the last one, oh, just kidding. We have two more links. We have the Waterjet. Unfortunate. Well, okay. I should have had ad block on or something. We'll see. But all right. So this is a Waterjet. They're actually cutting out like a piece of like titanium, I think. Yeah, titanium. Using this jet of garnet and water. The one that we have at the SEC looks a lot less fancier, and you don't typically see the cut like this, but super fun, super useful, and pretty easy to do. All right. And then last one, 5-axis CNC. So this is a lot like the CNC mill I was talking about, but instead now this can also rotate the tool in different directions, and you get a lot crazier geometry from this stuff. Just watch this. Man, that is so fun. Um, but yeah, you can like watch a lot of these videos by yourself. It's super satisfying as you can see from like the 4 videos I showed you. But let's keep going. So I'll go a little bit more in depth as to what the mill does. So with the mill, you can like carve out pockets. You can also face off like a a piece of metal and so on and so forth. So some common milling operations, at least that we use in robo jackets. The first one that I mentioned was like facing, right? So that's like you're cutting perpendicular to the rotation, right? You can like essentially if you have a block like this, right? Yeah, you can just shave off a part by moving the end mill, moving the part rather towards the end mill, and it'll just cut some stuff right off, right? So it'll look a little bit like that. On the other hand, like there's something called face milling. I actually confuse those two terms all the time, but essentially, like with a face mill, instead of cutting this way, you're cutting like this. So you're basically just getting rid of anything that's on top. Another one is drilling. So it's just creating holes. It's just like a drill, but what's nice about the CNC is you can, or the mills that we use is you can program them to, I guess, plunge and pull out like repeatedly by itself. And yeah, that's super nice. There's something also called pocketing. So this is like when you're cutting a contour in the center. So for an end mill, so like on the right, you can see like those pockets, both like that circular one and that like what is that like that pentagon? I can count 5 sides. Yeah, yeah. Like that little pentagon shape over there. That's what you call pocketing, and that's just like you can cut whatever contour you want in there. And this is super helpful, especially for when you have like a bearing, because what's really nice about mills specifically, at least the ones that we have in the shop, is they can manage some very tight tolerances. And for bearings, you want those tolerances to like be very precise, just because if you put it too tight, then the bearing isn't going to perform as well, and you can actually get failure much sooner. I've encountered that before. And if you make it too loose, it'll just slip right out, and it's not going to do its job. All right. The other one that's a little less common because we don't really have a lot of power tapping tools is you can actually tap using a mill. And what's nicer about this is that you don't have to do it by hand because tapping manually is kind of a pain in the butt, not gonna lie. Okay, now I'll talk a little bit about like the different kinds of end mills. Essentially, like we mostly just use like square end mills. You'll see them all over the shop, and they can come in all sorts of flavors, like 2, 3 flutes, and flutes just refers to like the number of cutting edges there are over here. I'll get into what exactly like each of those I guess flutes like actually are used for, right? They're very material dependent, but here's a nice little link for you to look at that just goes over what the basics of an end mill are. Like, gotta be honest, I have never really used any of the, what's it called? These angles or a lot of this terminology, other than like if you need to punch it into like something like a feed speed wizard, as they call it, right? You can feed in like the parameters of like what your material is that you're cutting into, the material of your tool, as well as like the number of flutes and like the length of the flute and so on and so forth and diameter. And it'll give you like what feed rate you should like actually be pushing the end mill through the material and what speed you're actually supposed to be rotating that end mill to get a nice cut. And like over here, it'll just go over like all these different types of end mills. So like on the left, the one I talked about before, square end mills, these are the most common ones. So as the name kind of implies, you get like this right angle as you're cutting into things, right? And this is used for like slotting, profiling, and like plunge cutting. There's also like specific end mills for cutting keyways into shafts. We don't use them as often. I actually don't remember. Actually, we might have some keyway end mills just because we have a huge cabinet full of like old garbage that professor like years ago just gave to us because they didn't need it anymore. There's also ball end mills. You can read more what each of them do, but the main ones I want you to remember are like square end mills, roughing end mills, and like ball end mills. So, and I guess like where is it? You can also get like different types of tapers, and you can get like counterbores and countersinks with these kinds of guys. But there's also like the roughing end mill kind of equivalent. So just like in a square end mill, you'll have like a right angle at this side, and that's just so you can like actually cut in the material into the material a lot quicker, but you won't have as nice a finish. And then you can actually like do the final push with like a nice square end mill, and it'll overall take a lot less time for you to actually mill the part in some cases, especially if you're CNCing and you have access to changing the tools very quickly. But yeah, that's pretty much it. You can go over these in your own time if you want, but those are essentially like the basic ones that we use in the RoboJackets shop. So since the main two materials that we use in the shop are aluminum and steel, like these are just like the ones that you have to look out for. So with aluminum, the type of end mill that you want to use are 2 flutes, and the material that you're going to want to use for aluminum is something called like high-speed steel or carbide. So I think that's like tungsten carbide or something like that. You also want to use, if you want a coating on your end mill, you should be using like this titanium nitride coating, so it'll look golden color. And on the other hand, like for steel, you use more than 4 flutes. The material of the end mill has to be carbide, otherwise you're going to have some issues with actually like, you're cutting steel with steel. That's not going to go very well. You're either going to sacrifice the integrity of your part or the integrity of that end mill, and that is not very good. You'll also like either have like no coating or some other coating. So this one's titanium aluminum nitride or something like that, and it looks like very like dark black or sometimes purple. It really depends on what you're buying, but those are basically essentially the ones that you're going to be looking for in the shop. So why exactly do they have differences? So like with regards to like the number of flutes, right? For aluminum, that's 2 flutes, and then for steel, that's 4 plus. So whenever you're cutting anything with cutting aluminum, right, you actually need more space in between the cuts to prevent chips from sticking. Additionally, since aluminum heats up very quickly, like the added space just lets it cool down a little bit better. And because you're removing those hot chips a lot faster or a lot less often, you won't have that issue as much. What else? So another reason why we use like carbide instead of high-speed steel, like I was saying before, is just because like it's a lot stronger and a lot harder than high-speed steel, but it's a lot more expensive. So that's why we don't really have a lot of carbide end mills, but just use those for steel because high-speed steel isn't very great for cutting on steel. While you can use it as long as it's for like a softer steel, like it's not recommended, and we don't really have the budget to just be throwing high-speed steel end mills like out the willy-nilly. All right. Some other things. The reason why I mentioned the coatings before is that they also reduce like the affinity of the end mill with the cutting material, and it also reduces the heat transfer to the end mill, as well as the hardness. So those two materials I mentioned before, like that titanium nitride and titanium aluminum nitride, those are both ceramics, and ceramics tend to have very low thermal conductivities, right? And as a result of that, you're actually not heating like the carbide center or like the high-speed steel center as much, and you're not getting as much expansion. So that's really good. And it also, like if you're cutting something with like a titanium aluminum nitride onto like an aluminum part, since that aluminum wants to bond to that aluminum, that's not really recommended. So that's why you use a titanium nitride coating instead, if that makes a lot of sense, right? And the same thing with steel. Like if you have like a high-speed steel end mill, like the iron particles are going to want to stick together, like the carbon that's within the steel is going to want to stick together. So that's why you want coatings, especially. It'll actually increase the lifetime of your part as long as you're using them correctly. Yeah. So another thing that to address with regards to milling is there's two different types of ways that you can actually cut into it. So one of them is called conventional milling, and this is where you're actually like as you're moving the material towards you, right? You can imagine like the cutter is actually rotating with it, and it's like picking apart like in the it's going in the same direction, so it's not going to be what's it called? It's not going to result in like as good a finish. Actually, I'll get more into like why using each of them. So like with conventional milling, like if you need if the mill has like a lead screw or it's designed for conventional milling, or you want to have like a rough surface, like just go with conventional milling. And most of the manual mills, especially in like the SCC, end up having that lead screw and are designed for conventional milling. And lime mill. So do this whenever you can. That's when the I guess like you can kind of see on the right, the material and the cutter is moving in the same exact direction. Okay. Another couple of reasons why you use climb versus conventional. So like conventional ends up producing a worse finish. It can be a lot more precise because the deflection of the end mill is parallel to the cut. What I mean by that is like if you imagine like the end mill as being as kind of like a beam, right? And the material that you're cutting into is like applying a force. Because those forces aren't like in the same exact direction, you'll have a little bit of deflection in this direction, right? Of course, but you'll also have a little bit of deflection like this way, if that makes sense. So because you're not getting as much deflection like in the same directions for both of those reasons, right? You'll end up getting a lot less deflection in general from the end mill to the part, and you'll end up getting better, I guess, you'll get better, closer, more accurate cuts than you would typically get with like climb. The other thing is with climb milling, it reduces the tool and machine wear, right? And it has a better finish, but it can also be less precise due to deflection, right? Because the material cut and the material movement is in the exact same direction. It's kind of what I just said for like the last minute or so. That's exactly why climb milling is going to be less precise, right? And something that I would also like to point out is deflection is mainly a concern when you're using long and thin end mills. So kind of like with what I was saying before with the rigid beam, like you can imagine if you push the end mill up, right, you have a smaller, a shorter length end mill, the torque that you're going to be producing is going to be less, like with respect to the, I guess, the tool holder, right, just because you have less of a moment arm. And the same thing goes with this guy, right? If you increase the moment arm, you're going to be getting a higher torque. You're going to be getting a lot more deflection. The other thing is like with a thicker, I guess, piece of material, right? You're going to be getting a lot less deflection overall, just because that's just kind of how materials work, right? When you increase the cross-sectional area or the area moment of inertia of something, because there's just more material in general, you're going to get less deflection, if that makes sense. So, ergo, why you should be concerned about deflection with those types of end mills. Now, as I mentioned before, why do we do CAM and CNC, or why not like for everything we do? It's really nice because there's a lot more geometries that you have available to you. So like in that video that I showed you, there was that really nice, I think, motorcycle helmet, and I wouldn't recommend just wearing a helmet out of aluminum. That doesn't seem very safe to me, but I'm not a helmet expert. That's just my opinion. But like as you kind of saw in like that video, you can do some really crazy stuff if you have the machine program to do all that stuff for you. I can't imagine someone being able to do that manually without like years of experience and like just a lot of work just for like one simple part. It's just a lot faster and a lot easier to do with like a camera CNC. The other thing is like with regards to geometries, like if you look at the parts that you have on the right, in addition to that motorcycle helmet, a lot of these would just be impossible unless if you had the right tools, right experience, and a lot of time. So yeah, don't try to CNC anything, or don't try to do this manually if you have some crazy geometries like that. The other thing that I would like to point out is it reduces human error, and what I mean by that, it's not necessarily just human error, but like I guess precision of like the machines as well. Typically, they're a lot better calibrated when compared to like manual mills. And the other thing is that you can get much tighter tolerances because of these reduced errors. So like, for example, whenever we, make a pocket for a bearing, at least in RoboNav, we would typically do this on like a CNC just because those tolerances are a lot easier to get on there instead of like cutting a little bit, checking if the bearing fits, cutting a little bit more, checking if the bearing fits, and so on and so forth. The other thing about camming and CNCing is like if you have the same part like 50 different times, if you're doing it on a manual mill, that's going to be a huge pain in the butt. You're going to have to, you're going to have to do those cuts like over and over again. It's just going to save you a lot more time if you just do it all on a cam and CNC. But as I was saying before, the reason why we don't typically use cams and CNCs like for a lot of stuff is it also takes a long time to set up. Hence why if you have repeated parts, it's more recommended because that setup isn't going to be you're spreading the overhead of setup time essentially, right? Like that's a constant that you're adding to your entire machining process. So yeah, pretty much it, if that kind of makes sense. I know I jumbled my words up over there, but I hope you get the bigger picture. So you think you know how to drill. Another thing that I'd like to go over instead of just like talking about end mills like all day, just like different types of drill bits. So something that I want you guys to notice is that like not all drill bits can cut with their tip. So like as you can see on the right, this has like a bit of a flat edge if you see where my cursor is. And all this means is that you're probably going to have to make a smaller hole or use a smaller drill bit or something that does have center cutting. So just make sure you check on that before you actually start drilling with stuff. But other than that, it's like fairly simple. Like get the diameter you want, and that's pretty much it. Nothing crazy. This kind of leads into the second thing that I wanted to talk about. So like I said, you want to use a smaller drill bit. So we call these things pilot holes. And all pilot holes is just like a hole that's drilled into the workpiece before you actually drill the screw in, or if you want to make a bigger hole after that, right? With regards to pilot holes, like whenever you're like actually putting like a self-lathing screw, like as you can see on the right, I think that's just like a self-lathing screw that's being put into like wood or something. Like the rule of thumb is that the pilot hole should be the diameter as the core of the screw, and it just enables the threads of the screw to bite into the piece a lot easier. And also prevents the piece from like splitting apart. Like if you try like putting a huge screw into a piece of wood that doesn't have a pilot hole, it'll just split it apart immediately. Like you pretty much need to put a pilot hole when you're working with aluminum or with wood, sorry. Okay, another thing. I mentioned tapping before and how tapping my hand is a huge pain in the butt. So like essentially like with tapping, you're just creating internal threads. You use this whenever you want to have a bolt go into a part and just fasten without having a nut on the other side, right? And there's different kinds of flavors of tapping, like as you can see on the right. And let's see. So whenever you're like cutting the taps out, like it'll like determine the whole. Like whenever you're getting the hole size for like your taps, like you just look that up from like a spreadsheet, and you can cut the taps. What's it called? You can use the cutting taps to cut the threads into the hole instead. And forming taps, on the other hand, like as you can see on the right, is like it pushes materials out to form the threads, and typically you can use those for what's it called? Or maybe I have it the other way around for machining. I'll get into it a little bit later. I think there's also a video to show you with regards to this specific slide. So you can see what like tapping actually is up close. Yeah. So this video over here, it's just a guy like that teaches you how to tap. So like he's just holding like I think just like a regular like old cutting tap. But essentially like if you don't want to just like be trained in person, you can always look at this video up. I mean, just look at the guy. Like you can trust him to like teach you how to machine anything. Honestly, like the vibe I get from him, he's a very experienced machinist, so he knows what he's talking about. Just watch the video if you just want to like learn how to tap real quick, right? Okay, next slide. Some things about tapping is the angle of the cut as well. So like in a spiral flute, like as you can see over here, and I think these are what you can actually use like in a a machine like I'm not going to say drill press. I don't think you should be tapping on a drill press, but like in a mill, for example, or like with a what's it called? I think like IGBC has also used them, or RoboNav, sorry. We've also used them with our own what's it called? Battery powered drills, like those handheld ones. But essentially, like these spirals over here will push like the chips up. So whenever you're cutting material, like it's not like that material is going to go magically away. It needs some way to actually like get out. So like typically, like with a non-spiral flute, you'll have to do like 2 turns one direction, 1 turn the other, just to get those chips moving back and forth. And however, with like that spiral, because like it just constantly pushes the chip down, right? It's just going to be a lot easier, and you can do it like in one go. The one thing I will say is like the majority of our taps are spiral point, just because they're the strongest, they last us the longest, and because we have so many new members and I guess like old members that don't really know how to tap as well, right? You end up breaking a lot of taps, and you know what? That's completely fine, but that's the reason why we buy a lot of these spiral points, just because they will last us the longest for more bang for the buck, they say. The other thing with tapping is there's different types other than like the spiral and the cutting and the forming taps, right? So there's one called taper. So essentially like the taps don't begin cutting until like a little bit further down, right? So these cut the threads the best, and essentially like whenever you're cutting with like I guess a tapered one, like because you're not starting the threads until way later, like the full depth threads, you can't really use this for like the bottom of a hole, right? The other one that I'll mention is like the bottoming tap. This is the exact opposite. So like as you can see, like on the very right, the bottoming tap will have the full thread size like very close to the end of the tap. And this is where you can just like go into a hole, and if you want like 0.5 inches of thread for a 0.5 something inch hole, like please use one of these guys. So like usually when you're tapping stuff, you'll go in with like a taper tap and then finish it up with like a bottoming tap. But sometimes that can be a bit of a pain. So like you can also use what's known as a plug tap, and that's kind of in the middle. I'm sure there's more technicalities, and there's probably better reasons to use a plug tap. But honestly, like with what we have in the shop, like plug taps are pretty much spread, and they'll get you the job done a little bit quicker, just because you won't have to go in with taper and then bottom, and so on and so forth. All right. A couple quick tips with regards to tapping. This is really important, just because like speaking as someone who has broken taps himself, like I wish I kind of knew these before I started going into it. Like something that's really helpful is like you should chamfer the hole at least a little bit. Either you can use like a deburring tool if you really want, like something simple like that. But essentially like that lines up the tap a lot better, and you won't be going like into the hole like at an angle or anything, right? It'll make sure that it's pretty centered. The other thing is like if the hole was made using a Waterjet, right, and you're just like tapping like whatever sheet metal that you just cut out, you should also drill it out before you tap. The reason why is because whenever you are water jetting, since it's literally a jet of fluid, right, as the fluid moves further and further away from the nozzle of the water jet, it'll actually spread out a little bit. So you'll actually get a little bit of a taper as you cut into like any piece of metal. So in order to fix that, and so you don't have like too small a hole at the very bottom or too small a hole at the very top, just drill it out with like a hand drill or something before you tap it, just because it'll make things a lot easier. Another quick tip, and this applies to me specifically, smaller taps will break more easily, but larger taps will require more force. And that being said, like we do have a lot of different instruments for tapping in the shop itself. Like we have a huge jig. We didn't make it. It was definitely bought like, but essentially like you can go very overboard very quickly with smaller taps. So make sure you're using like a hand tapper or something instead of like one of those presses, or I forget what they're called. But essentially just like make sure you're using the right amount of torque and you're not overdoing things. The other thing I'd like to mention is like whenever you're designing like different tapped holes for the materials you're using, I will say like 440 to quarter 20, in Imperial is like the sweet spot of aluminum. Like if you go any bigger, it's going to be a lot harder and you're going to have to get a little bit more fancy with it. Like you can probably do it on a lathe a little bit easier, but we also don't really have the tools for that necessarily. But this is just like a rule of thumb. And kind of what I was saying before, like with those smaller taps breaking, we broke about 6 440 taps last year, and that is not an anomaly. That sounds about right for every single year that I've been a part of Robo Jackets, especially because like those taps are very small. We have like both the 3-pounders as well as like the RoboCup bots that specifically use like a lot of small fasteners. So that ends up being the reason why we break those taps. It's not really the fault of the user. It's just those things are very fragile. The other thing is like this is another, what's it called? Rule of thumb. So like leave the bare minimum radius of your tap on either side of the hole if it's near an edge. This is just a bit of like, I don't want to say common sense because it's not, this isn't something I think about all the time, but essentially just like leave enough material between your hole and like the edge of your part so that you can actually like cut threads into it, if you will. All right. Okay, the last machine that will go in depth, I think, I may be wrong about that. Don't I'm not going to place any bets or anything. Don't hold me accountable to that. Is like the lathe. We don't use this as often in Robo Jackets, but like for cutting grooves into shafts, for example, or cutting, pretty much anything with shafts, really, like anything that you're like making gearboxes out for, like you're gonna have to use a lathe, right? And basically, like over here, you just have a bunch of different like cutting tools that are typically used with the lathe. The parting tool is used to like just cut like a square groove into it, or you can just completely take that part off of the lathe if you go all the way in. These other cutting tools are if you just want to have like an angled cut or just like a straight cut for whatever you're doing. I don't think I'll go too in depth on this. Like I don't remember the specifics of each one, but like as you're like lathing, this will make a lot more sense as you go, and you'll kind of understand what tools to use for whatever. Like for example, like these tools like in the middle, like you can see these are for like these flat faces, if that makes sense. The other thing that you can do with lathes that's super helpful is threading. So like we do have different like threading tools that we have in the shop, and all you have to really do with a lathe is just get it at the right feeds and speeds. So that way, as you're passing the threading tool through the threads, right, they'll be at just the right rate so that these threads don't like overlap and all that stuff, and they're the right size. Oh, kind of like what I was saying before, like just saying again, like parting tool just cuts a deep groove into the part, and you can just like make a new part from this stock, right? So if you have like a huge bar of aluminum and you only make a part over here, you can use a parting tool and just like snap it. I'm not going to sacrifice this pencil. I'm not. What am I thinking? From that piece of stock, right? Easy peasy. Facing, like kind of what I was saying before, like those are those perpendicular flat parts that you're lathing out, right? And this is just for like, I'm going to give an example of like a gear, since those things are like pretty thick a lot of the time, or even like for not retaining rings or shaft collars, I guess. No, but you don't need to make grooves for those guys. Like, let's just say you have a gear, right? And instead of like using a parting tool for like every single thing and like going out with that, you can just use a facing tool and just like do several passes like in more and more inwards until you get like the right sized inner diameter, and that's really where you can do some fancy stuff. Turning, this is like the basic I guess operation. This is pretty much what you're doing all the time when you're on a lathe. So it'll reduce the radius of the part that you're at an area, and you just reduce this to from the diameter of the stock to like the desired diameter. And if you remember in like that video about the Rook, right, like it essentially you saw like the turning tool like get closer and closer to the diameter as it's going through the what's it called, to wherever it needs to be. And this is really where like the fancy CNC stuff like comes into to play, right? Like you can cut whatever grooves you want just by turning them. Okay, last machine. This is why I told you not to hold me accountable to this. Yeah, I knew I was missing something. Waterjet. Since this is the one that we use the most, I'll be honest, like in my opinion, the process that you go through for water jetting is like you create a DXF file. So like in Inventor, you can right click the face of whatever part you're on and just like say export to DXF, put it on a thumb drive, go to the Waterjet, and then just put that file right in there. Generally with a Waterjet, unless you have some really fancy stuff like I think they have in the Aero Makerspace, you can only really cut 2D profiles on a Waterjet. The reason why I say generally is because like in the SEC we only have that capability, nothing else too crazy. Oh, I guess like it's also the Invention Studio that has one. But essentially like the Waterjet, if you get like a fancier one, you can actually tilt the head, kind of like what you were seeing with like the 5-axis CNC, but not as crazy. Like you can get some angled cuts instead, and that's where you like want to make tapers that are what's it called? That are intentional, not like the unintentional taper that you get just by the fact that the water, that the fluid is like splitting off or is getting a little bit greater in diameter. Okay, now last thing about the machines, right? So limitations. First and foremost, people are not perfect. I have mentioned several times to you before that I have broken stuff. And whenever things break in the shop, always make sure to report it to the shop manager, just because like people don't want to go into the shop and then not have the tools that they want to work with, right? There's no shame in breaking stuff. I'll just be honest with that. And also like with regards to parts, another thing with like people aren't perfect, right, is like if you're using like a manual mill or a manual lathe or like cutting things manually, like you're going to make mistakes. Like just plan accordingly and do whatever. Some other thing is like everything is somewhat elastic. What this really means is like, remember with like the deflection, right? Things are going to want to like bounce back into place. So sometimes you'll miss tolerances just by a very little bit just because that material is going to be pushing back off, if that makes sense. Tools wear down. So a lot of the times with the end mills, you might not be cutting as nicely and you might be getting like a bit of a screechy sound. I don't want to say like screechy, but you'll know it when you hear it, right? Like you'll notice when you should probably get that thing replaced when you're actually using it. And with that, like what you need to keep that into mind is that you might not get the tolerances you want with, let's say, like something that's been worn down for a long time. It's not like you can just put it into a CNC and you're going to get the magic, perfect dimensions if your tools aren't exactly to spec. The other thing that's important to note is that machines themselves might not be ideally calibrated. What I mean by that is like both like in the Waterjet, the mills, especially the mills and the lathe, they might not always be able, like they'll have a bit of backlash sometimes. So like if you move forward and try moving a little bit back, it will actually think you moved a little bit further than that, just because it takes a little bit of time to whatever. You'll notice, you'll know what I mean when you're actually like milling. You'll notice that like if you like change the direction of the mill, sometimes the actual, what's it called? The digital readout is not going to be exactly right. So just take that into consideration when you're milling. And tapers, kind of like what I was saying with the Waterjet, that stream of water is going to split off or like get a little bit wider as it goes further down the part. And that's just something you need to take into account, especially when you're cutting something that's like 1-inch steel. Like we've done that in RoboNav like fairly recently, and you need to like either grind that down or just get a couple cuts in, do whatever you need to make sure that those tapers aren't a problem. But just keep these in mind. Like you'll know it when you see it. Okay. Other things about machining in general. I was mentioning before with like bearings specifically because those tolerances can get very tight. So those tolerances are going to vary greatly depending on what part you're making and how you actually want this part to interact with other stuff. And essentially, like what this boils down to is we have there's like a system out there for defining what kinds of fits you want. So first you have like a clearance fit. Like you can imagine like with a clearance fit, you have like a big hole and you have a very small shaft and you have a little bit of, I guess, like looseness to it, right? So with clearance fit, you can have like a sliding fit, so it's just like barely there, or like a running fit where it's like, it's pretty noticeable. You can use this for like bolts, for example. The other thing is like something called a transition fit. So like that's a lot more like the sliding fit that I mentioned before, but like essentially like it fits there perfectly. These are going to be the tightest tolerances, if I recall correctly, that you need to manage. The other one is interference fit. I think we covered this a few lectures ago. So essentially, like you can make the hole a little bit smaller than the shaft and then just force it in, or let's say like with a bearing, sometimes you can force it in. That's not ideal sometimes, but you'll know when you need to use an interference whenever you're working with parts. So like for example, puzzle fits will go into the interference fit category, and you can literally just look up like a fit calculator to get you all that stuff. So, oh yeah, that's exactly what I was talking about before. Sorry, forgot. They branched off into 2 different slides. So kind of what I was talking about before, like this is how you can see it visually instead of just me waving my hands around with like some pencils and just an OK symbol in my hand. All right. So like on the left, you see like a clearance fit. You see like a pretty clear like difference between like the shaft and the hole. Oh, something that I'm going to mention is that there's actually 2 different tolerance systems. So whenever you look up like what tolerance you need, like usually I just look it up on Wikipedia if I want like a clearance fit or something. Let's say like you know what your dimensions of your shaft is, but you need to make a hole. You can use like the shaft system to be able to specify what tolerance you need for that hole, for example. So in that one, the shaft stays the same dimension while the hole changes. On the other hand, like there's the hole system. So this is where it's the exact opposite. The hole is at a nominal diameter. We know what that is. And you're trying to machine a shaft to fit in there with whatever tolerance or with whatever fit you want, right? And like I mentioned before, you can just like look up a fit calculator. Like you can literally say like, what is the symbol for like transition fit for a shaft, right? And you can just go ahead. You can go to this website, but usually I just like look it up and things like this will pop up. And you can just play around with this yeah, you can see like I've already clicked this link over here before. It's purple. So that's pretty much it when it comes to fits, I believe. The last thing that I kind of want to mention is you can also make external threads with a die. So typically we use this for like really, really thick parts. Where you want to like either, what's it called? You want to cut grooves into it, like just like in a bolt, right? You can make external threads with like a die, or you can just do it with a lathe, which is, I think, the preferred method in my opinion, especially if you have like some really thick bolts, because this can be a pain in the butt to actually do like manually. Especially like if I recall correctly, Robo Racing a couple years back was machining some shafts for their steering system. And an issue that they had with actually like trying to use the what's it called? These external dies is that even if you're slightly off at an angle, that's going to propagate down a lot more for the longer length of the threads that you're using, and that just becomes an issue. Most of the time, like just try to avoid it if you can. And a lot of times you can just get away with using bolt. Just use a bolt, like it says on there. Finally, the last thing that I want to mention is like the normal tolerances that you can get on machines, right? So kind of what I was mentioning before, like the CNC is a little bit closer. But essentially like with a manual mill and a lathe, you'll get like 0.005, like you'll get around that dimension as long as you're careful. What's it called? With a CNC, you'll get to like 1/1000th of an inch. That's really nice. You'll need to measure your tool, and you need to like make sure that, what's it called? You're calibrating everything before you actually go into cutting the part. And like, I'll be honest, like the CNC is probably the best you're going to get in the shop, unless if you like outsource it to something fancier. Now with the Waterjet, it really depends on the taper. So like what I mean is like for thicker parts, the tolerances are going to be a little bit looser just because it's going to be going out on an angle. In general, like the Waterjet is worse than the mill, right? But like on the other hand, if you're just like laser cutting something like in the Invention Studio for like a thin like wooden part, typically you'll get something pretty close. Again, probably a little bit worse than the manual mill, but that's just something you have to keep into consideration. And it'll also leave a little bit of a worse finish if you really care about that. That really depends on like if you're running like a shaft through it and it's going to be rotating. All right. So which machine should I use? This will kind of become ingrained into your design toolbox. So like as you're working with these machines and working with designing parts for use in these machines, right? You'll kind of understand when to use them as necessary and how to design the other way. So with a lathe, you're going to do that. You're going to use it whenever your part contains like concentric cylinders or it's axially symmetric, right? So like with any sort of shaft, you'll end up getting that kind of symmetry, and you'll be using it on a lathe, guaranteed. Waterjet is like whenever you have like a 2D profile you need to cut. It's fairly self-explanatory. And mill, this is like the fanciest one. You can use this for a whole bunch of stuff. Honestly, like, and I've done this in the past just to like learn how to use the CNC mill. Anything you can do on the waterjet, you can do on a mill, but better. But you can also do some other stuff. Like you can do like you can face off like a part. You can do like some complicated grooves, like in 3 dimensions. Honestly, it's like pretty limitless what you could do on a mill, especially if it's a CNC. The last thing I'd like to mention is like if you have any questions about like the machines or you're not comfortable with what you're working on, like always just like first, like if you're in the shop, like ask your mech lead like what to do, right? It's better to be safe than sorry. And if you have other questions about like how to design parts or need additional help, you can always like ask in mechanical AMA or the shop channels in Slack, right? The other thing that I'd like to mention is that stock normally comes oversized, but you can always like check the manufacturer's website to see what like their tolerances that they specify like in quality assurance as they're like shipping things out are. So yeah, pretty much. So like from experience, I don't remember who wrote this, but this sounds about right, honestly. 1/4 inch like thick stock or like round stock will vary from like 0.253 to 0.265, but it's around 0.255, and that's just because like it's a lot easier to subtract something than it is to add, right? Like once you've cut too far, that's a huge problem, and you're not going to be able to use that part, and you'll probably have to get a new piece of stock for it. So with that being said, it is time to play Kahoots. Let me, yeah, just go to Kahoot and I will get this guy back up real quick. I think classic. Yes, so the link is just this guy over here. How many people do we have today?
Got up to 15 at one point. I think it's 14 right now.
Okay, no worries. Sorry, I'll get back to this so you can actually see.
Oh, wait, hold on. We got some people who left.
Yeah, I think there's 12 people now.
It's 12 now.
Okay. Yeah. That's okay. It happens, especially like during this time of year. Things get very busy, so like it's all good. We understand. Oh, we got Mike Wazowski playing. Damn, son. Okay, now I think we're ready. So let's get going, I guess. So week 5. Let's start right now. Question: what kind of tap do you use to make threads at the bottom of a hole? Excellent. Yeah, it's just as the name implies. Use a bottoming one just because the threads are as close to the actual thickness of the threads at the very end of the tap. So it's pretty easy to remember. Bottoming, it's in the name. Like, let's go next question. Okay. How many flutes should an end mill have for steel? Do they have 1 flute end mills?
No, what would that be?
Okay, if you excuse me, I'm just gonna look this up real quick. 1 flute.
I don't think that's a thing. No, there's no way.
There's no. Oh, it's a thing.
Huh.
That looks exactly what I thought it was gonna be. It must not be very useful. I've never seen one before. Okay, let's get back to Kahoot. Sorry, guys. All right, next question. Which tool do you use for this part? Okay. Can you guys see that? Hell yeah, yeah, it's a lathe. Just because it's axisymmetric, right? I think for that one, it's just cutting a groove right into it with two tapers in here, right? You'd use a facing tool and then probably like a turning tool, right? Okay, next question. All right, you guys are doing well. Glad to see it. What is this operation called? This is probably a mill, if I recall. Oh, just kidding. I don't remember the order of the questions. Oops. Yes, very nice, very nice. It's literally just like you're taking the face off of like whatever rough cut you just made from the stock. Very good. Okay, next question. Is this climb milling? Yes, that's true. It's going in the same direction as the part is cutting almost. Sorry, I think
The
I might
way
have
I think of
jumbled
it,
my. Oh, go ahead.
can you click show media?
Yep.
The way I think of it is like if you're a climber and you're climbing on a wall, it's like it's grabbing the wall and pushing it in. That's just how I think of it. So if that helps,
That's a
then
very good, I guess, like rule of thumb. That's actually super helpful. I wouldn't have gotten that. Okay, let's go. What operation is this?
oh, we got rid of the close answer.
Yes, yes, because that always confused me, gotta be honest. Yeah, face milling. So, real quick, we actually have a lot of these guys in the shop now because, like I mentioned, I think it was like a computer science professor had a huge machine shop where they had a bunch of different gadgets to work with, and he never ended up using. So we actually like, since I was the shop manager at the time that we got it, if I recall correctly, like we have like a 9-inch diameter face mill that like, if I recall correctly, costs like $2,000. Don't at me on that one, but yeah, it's crazy. These things get very expensive, but they're really useful for taking the face off of whatever you're machining. Okay, next question. All right, what machine is this? Very nice. Yeah, horizontal bandsaw just because that actual, I guess, belt that's like running through the material is parallel to the ground, right? All right, next question. What machine is this?
This is a tough one if you haven't actually seen one in person.
Yes, a Waterjet.
Yeah.
I will say, even though we didn't mention CNC router, this looks very similar to one, I'll be honest. Although this is definitely a Waterjet because there's some slats and stuff. But yeah, if you said CNC router, like you're still close. You got it. Waterjet was the right answer though. Next question. When should you use a CNC? Yeah, it's when you have unusual geometry for a lot of the time. There are more reasons than that. I'll be honest, like when you don't want to use the manual mill, even though that's technically correct, most of the time you'd always want to use a manual mill as opposed to a CNC if you can get by it, just because it's a huge pain in the butt to actually like CNC something. You have to program it and everything. You have to like calibrate it for the tool diameters. It's a huge mess, in my opinion. All right, let's keep going. Next question. Which materials can use the titanium aluminum nitride and mill in? So this is the coating. Yes, it's definitely steel. Remember, because this aluminum is going to want to bond to this aluminum, and you'll have issues with wear and tear on your coating instead. So please just use it for a steel if you can. All right, next question. If I want my parts to stay together, stay stuck together, what do I use? You might also you can technically
Yes.
use Loctite. Oh, they're both right answers.
They're both.
Yeah. That makes sense. Although Loctite is hella expensive, please do not use Loctite for everything. That'd be crazy. But it's true. You can do that. All right, next question. All right. What is pocketing? Stealing things from the river jacket. Please do not do that. Yeah, you guys all got it right. Very nice.
100%. Here we go.
Bring a shape into the inside of your part. Let's go. Next question. Let's go.
Last question.
Who do you contact when you break a tool?
Oh, good. We did update this.
Wait, why is Kristaps the treasurer still? What?
Oh, what? I thought we updated that.
I mean, that's
Who is
technically
now? Oh, it's Christopher Flowers, right?
yeah. It's Christopher.
Okay.
Kristaps has graduated 2 years ago. That's interesting. All right, yeah, it's VJ, the shop manager. Okay. And next question, or I guess like the
Here we go.
one.
See,
Monkey, Monk. I got Kiertik. All right. Is this Jeff? Very nicely done.
hey, congrats.
Congrats.
13 out of 13. Very impressive.
Very well done, guys. Only one person got 13 out of 13. Wow, that's crazy. Nicely done. Well, that's pretty much it for just the Kahoot. There shouldn't be anything else on the machining lecture slides, but we do have a CAD guide out for you guys this time. It's a little bit different than usual, I will say. Instead of being formatted as a, what's it called?
Here, I'll send the links.
Okay, you got it.
Yeah.
But essentially, like with this guy, instead of being a step-by-step instruction, you'll actually get a STL file that you will need to, I think it's either recreate or make some changes to, right? But essentially, you'll be given some images and some dimensions, and you'll have to figure out how to actually CAD this from scratch by yourself. So this will be really fun. Like I've had to do this for a class last year. I actually highly recommend it. I'm gonna do a quick plug. If you're an ME, I think it's ME 4042, Gautech. Yeah, interactive computer-aided design and computer-aided engineering. This will teach you a lot of like advanced CAD and some FEA stuff if you want to work with that, so simulation. And for my final project, me and my group members recreated a, what's it called? A harness, or like shoot, what's it called? A carabiner for rock climbing. And those things actually have crazier geometries than you'd expect. But I will say, like, this is really fun. I personally enjoy remaking stuff in CAD, and you guys will too if you do this CAD guide. Okay? So we'll just stay on here for a little bit longer, I think. And that should be the end of that. So if you guys have any questions, we'll stick around for just a while longer, if that's all right with you guys. Okay?
Yeah, and
Thanks.
just so you guys know, those pictures on the CAD guide are just like to clear up some questions that you might have about what the dimensions are referring to. So you should have all the information you need, but if you are wondering about anything, we're here for you. So just let us know.